Have you ever looked up at the night sky and wondered about the universe's true nature? Beyond the stars and galaxies, there's a bigger question: does the universe itself have a shape? We live inside this cosmic structure, unable to step outside and see its form, like trying to figure out the shape of your own house from the inside. The answer isn't just about geometry, it's about the fate of everything. The universe's shape dictates how light travels, how galaxies move, and even how the cosmos might end. Imagine ancient sailors thinking the world was flat, only to discover it's a sphere. Could our universe be similar, finite yet without an edge? This quest is a testament to human curiosity. We build telescopes and satellites to explore not just new worlds, but the rules that govern reality. The search for the universe's shape is a journey through the greatest ideas of modern science. To talk about the universe's shape, we must rethink what space is. Einstein showed us that space and time are woven together into a four-dimensional fabric, space-time. This fabric bends and stretches, shaped by gravity, not as a force but as the warping of space-time by mass and energy. Picture a heavy ball on a rubber sheet. It curves the surface, and smaller objects follow those curves. Our sun warps space-time, guiding planets in their orbits. Even you and I make tiny dimples in this cosmic fabric. Matter and energy don't just exist in space, they shape it. The total amount of stuff in the universe determines the overall curvature of space-time. So when we ask about the universe's shape, we're really asking about the grand-scale curvature of this cosmic fabric. It's a cosmic dance between matter and geometry, and we're just learning the steps. What shapes can the universe take? Einstein's equations give us three main options: flat, closed, or open. A flat universe is like an infinite sheet of paper. Parallel lines stay parallel and triangles add up to 180 degrees. It's perfectly balanced, with just enough matter to halt expansion only after infinite time. A closed universe is like the surface of a sphere. No edges but finite. Parallel lines eventually meet, and triangles add up to more than 180 degrees. This universe would eventually stop expanding and collapse. An open universe is like a saddle. Negative curvature. Parallel lines diverge, triangles add up to less than 180 degrees, and the universe expands forever. Each shape depends on the universe's total density of matter and energy. The geometry isn't just math, it determines the universe's destiny. Which one do we live in? The answer is written in the sky. Let's see how we measure it. How do we measure the universe's shape from our tiny corner? Enter the cosmic microwave background, or CMB. The afterglow of the Big Bang. For hundreds of thousands of years, the universe was a hot, dense fog. When it cooled, light broke free, and has been traveling ever since. This ancient light, now stretched into microwaves, fills the cosmos and carries tiny temperature fluctuations, seeds of all structure we see today. These hot and cold spots in the CMB are crucial. We know their original size, so by measuring how big they appear now, we can deduce the curvature of space. It's like looking at a coin at the bottom of a pool. The water shape changes how the coin looks. Sensitive instruments like the Planck satellite map these fluctuations with incredible precision. By comparing the apparent and actual sizes of these spots, we measure the universe's geometry. The CMB is our ultimate cosmic ruler. So, what do the measurements say? Decades of observations, Kobe, WMAP, Planck, show the CMB spots are exactly the size they should be in a flat universe. On the largest scales, our universe appears to have zero curvature. Cosmic triangles add up to 180 degrees and parallel lines stay parallel. This means the total matter and energy is astonishingly close to the critical density. But there's a tiny margin of error. The universe could be perfectly flat, or just so vast that any curvature is undetectable. To refine this, we also study galaxy clustering and distant supernovae, which help map the universe's expansion and shape. All evidence points to a universe that's flat, or so close we can't tell the difference. But this near-perfect flatness is itself a puzzle. It suggests something, like cosmic inflation, stretched the universe flat in its earliest moments. The mystery deepens. The universe's shape is tied to its fate. A closed universe would eventually collapse in a fiery Big Crunch. An open or flat universe would expand forever, ending in a cold, dark Big Freeze. For decades, scientists debated which ending awaited us. But in the late 1990s, astronomers discovered the universe's expansion is accelerating, driven by a mysterious force called dark energy. Dark energy now dominates the cosmos, making up about 70% of its energy. Even if the universe is closed, dark energy's push could prevent collapse. The evidence now points to an accelerated big freeze. Galaxies will drift apart, stars will die, and the universe will become cold and empty. Our cosmic fate is isolation and darkness, with expansion speeding up forever. The universe's shape and its ultimate destiny are forever linked. Our measurements say the observable universe is flat, but that's just the part we can see. What if we're like ants on a giant balloon, mistaking a tiny patch for the whole? The universe could be locally flat but globally curved. This leads to topology, the study of space's global shape. A flat universe could be infinite, or it could loop back on itself like a donut. In a donut-shaped universe, traveling far enough in one direction could bring you back to your starting point. Scientists search for repeating patterns in the CMB that would reveal such a shape, but so far no evidence has been found. The universe could be a Mobius strip or have other exotic topologies, mathematically possible but currently undetectable. For now, the simplest answer is an infinite flat plane, but the true shape may be stranger than we imagine. The search continues. The universe's flatness leads to even wilder ideas. Cosmic inflation suggests our universe is just one bubble in a vast multiverse. Each bubble could have its own laws of physics, its own fate, some like ours, others wildly different. We can't visit these other universes, but the theory helps explain why our universe seems so perfectly tuned for life. This is the anthropic principle. We find ourselves in a universe suited for life because it's the only kind we could exist in. The multiverse is a bold idea, hard to test, but a natural consequence of our best theories. These concepts blur the line between science and philosophy, pushing the boundaries of what we can know. The true shape of our universe may be just one detail in a much grander cosmic tapestry. We started with a simple question: does the universe have a shape? We've measured, mapped, and peered into its fate. The evidence points to a flat, ever-expanding universe destined for a cold, dark eternity, but the story isn't over. Every answer opens new questions. Why is the universe so flat? What is dark energy? Is our universe infinite or does it loop back on itself? New telescopes and experiments will probe deeper, searching for clues in the CMB and the distribution of galaxies. The quest to understand the universe's shape is part of humanity's grand adventure, mapping the ultimate territory. We live in a special moment, able to ask these questions and seek answers. The story of the universe's shape is still being written, and the next chapter may be even more astonishing.